The universe is vast, unimaginably so. Our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away. To get there with our fastest current technology would take tens of thousands of years. That's a long road trip, longer than all of recorded human history. So, how do we cross these cosmic oceans? How does a fragile, short-lived species like ours ever hope to set foot on a world orbiting another star? This question has captivated our imaginations for generations. It's the stuff of our grandest stories, our most audacious dreams. We look up at the star-dusted canvas of the night sky, and we don't just see points of light, we see destinations. This is where a profound idea enters the picture, borrowed from nature and supercharged by science fiction. What if we didn't have to be awake for the journey? What if we could simply sleep through it? Not the restless sleep of a single night, but a deep, dreamless slumber lasting decades or even centuries. The ship would travel on, its silent crew suspended in time, their biological clocks paused. They would age only a few days while entire empires could rise and fall back on Earth. This is the promise of cryosleep, a concept that bridges the gap between our ambition to explore and the biological limits of our bodies. The allure is undeniable. Think about it. You could board a starship, say goodbye to a world you know, and then wake up in a completely new solar system. The starlight filtering through the viewport would not be from our sun, but from a different star. The planets outside would be alien, their colors unknown, their continents unknown. Cryosleep transforms space travel from a multi-generational crawl into a single lifetime's leap. It's a passport to the stars, a way to cheat the tyranny of time and distance. It makes the seemingly impossible possible. So, what exactly is cryosleep? Let's break it down. The word itself gives us clues. Cryo comes from the Greek word for cold, and sleep is, well, sleep. In its most popular science fiction form, cryosleep is a state of deep hibernation induced by radically lowering a person's body temperature. The goal is to slow down all of life's processes to a near standstill. Think of it like putting your body in a state of suspended animation. Your metabolism, the chemical engine that powers your cells, would slow to a mere fraction of its normal rate. You wouldn't need to eat, drink, or even breathe in the conventional sense. You would just wait. In our favorite stories, the technology is often sleek and flawless. An astronaut steps into a pod, a cool mist descends, and they drift into a peaceful slumber. The ship's computer monitors their vital signs for the duration of the journey, ensuring everything remains stable. When the ship nears its destination, the pod gently warms up, and the astronaut awakens, feeling perhaps a little groggy but otherwise perfectly fine. This fictional portrayal makes it look as easy as taking a nap on a long flight. However, the reality is far more complex, and for now, remains firmly in the realm of theory. When we ponder the challenge of human hibernation, we're not starting from scratch. Nature has been running this experiment for millions of years. Look at the wood frog. This small amphibian can survive being frozen solid during the winter. Heart stops. Breathing ceases. Up to 70% of the water in its body turns to ice. How does it do this without dying? The frog's liver produces massive amounts of glucose that flood the cells. That glucose acts as a natural cryoprotectant, preventing cellular dehydration and ensuring ice forms outside, not inside, the cells. When spring arrives, the frog thaws and hops away as if nothing happened. Bears enter a state of torpor for months. They lower body temperature by only a few degrees and radically reduce metabolism. They don't freeze. Their metabolism plummets and they don't eat, drink, or urinate for the winter. A human in a similar state would risk catastrophic muscle loss and bone density depletion if we don't solve recycling and protection mechanisms. So far, our real achievements are medical. Therapeutic hypothermia used after cardiac arrest or stroke. We can cool someone safely for a day or two to reduce brain damage. We can cryopreserve small biological samples, sperm, eggs, embryos, but not a whole complex organism or an intact 1.4 kilograms brain. Even if we could prevent ice, introducing cryoprotectant systemically raises toxicity and unknown long-term effects. The biggest biological question is the brain. Would memories and identity survive? The dream of cryosleep pushes science forward. Small discoveries, organ preservation, engineered torpor could transform medicine and one day might let us wake to a different star.